Welcome to another podcast. In this episode, we're going to be taking a look at what are called t-axis translation formulas for the Laplace transform. Now, I want to start out by just sort of posing a little bit of a quandary that we've gotten ourselves into here. If I look at the Laplace transform of the Heaviside function, that's equal to 1 over s. And if I look at the Laplace transform of the function 1, that's also equal to 1 over s. Both of these where s is greater than 0. So the quandary here is, okay, what if I ask you what is the inverse transform of 1 over s? Which answer do you give me? This goes to the uniqueness of the inverse transform. And that turns out to be a big deal. We like for inverse processes to be unique. And in fact, we've kind of been doing this the wrong way up until now, in the sense that even though none of our problems involved step functions or the Heaviside function, we've been talking about this problem, at least in terms of the inverse transform, without really considering what could go wrong. And so we're actually going to do that in this video. The integral for the transform of the function f, if you recall, is the integral from 0 to infinity of f of t e to the minus st dt. This formula does not care what happens before t equal to 0. The integral is only aware of the function values beginning at t equal to 0 on to infinity. So if something odd happens before 0, completely doesn't matter. Take, for instance, this function. So I'm going to look at one function here. I'm going to look at a different function here. So the function on the left, suppose that it is this one here. It's doing all sorts of crazy stuff. And then it's just kind of a nice little slow gentle curve from then on. So this is a function f of t. Here is the function g of t. Say the function g of t comes in and does the exact same thing as f of t from then on. Then what we've just discovered is the Laplace transforms of f of t and g of t will be exactly the same. Which means that if we want their inverse images to be the same, then we have to act like none of this over here matters. So I'm getting rid of all that happened before, scrubbing it away. None of this mattered. And the way that we do that is by saying, okay, really what this is our function didn't even begin until 0. So for the purpose of uniqueness, if I ask you what is the inverse transform of the Laplace transform of f of s, what you're going to tell me is that that is u of t times f of t. So it's sort of an aside here. If step functions are involved, you must give me this as your response. In other words, if I ask you what is the Laplace transform of u of t f of t, we know that to be f of s, and to make the inverse work, these two have to be paired up. They have to work in both directions. Alright, this is going to sort of lead us into a discussion here of a theorem, or if you will, maybe just a claim of a formula here. And that is, if I take the Laplace transform of the Heaviside function, or the unit step function, times a function that shares the same shift, then the transform of that produces an exponential. The way to think of this is if you multiply by an exponential in the S domain, then that produces a t-axis translation in the time domain. So this is a t-axis translation. Now, to show this, consider if we're just going to go by the definition here, with the integral from 0 to infinity of h of t minus a, f of t minus a, e to the minus st dt. This is the definition of the Laplace transform. That would be equal to, I'm going to do a change of variables here. I'm going to let v be equal to t minus a. So this integral will become the integral from, let's talk about the limits here. When t is 0, then v is negative a, and the upper limit will still be infinity. And then this will be h of v, f of v, e to the minus s. I can replace t with v plus a, and then dt becomes dv. So if I do a simple u substitution, that's what I end up with. And the way that the Heaviside function is defined, it doesn't turn on until time equal to 0, which means that the integral itself doesn't start until 0. And when you get to 0, the Heaviside function has a value of 1. So this is just equal to 1. And so I would have f of v e to the minus sv. Now if you look here, I have an e to the minus as. I'm going to factor that out. The reason I can do that is because the integral here is with respect to v. And so if you look at what happens, then the piece in blue there is simply the formula for the Laplace transform of the function f, which we would call capital F. So this is a big formula, one that you're definitely going to want to commit to memory. And one of the immediate repercussions of that is I can define a special function called the unit interval, or the unit box function. So the unit interval or unit box function is given by the function h of a b of t, but it's defined as the interval here where you'll get 0 for t less than or equal to a, 1 for t between a and b, and then it's 0 for t after b. In terms of a picture, I'll just use this space to the left here. Just to get a picture of this. If I have a and b, then the unit step function or unit box function is 0 up until the point a, then it's 1 between a and b, and then it's 0 thereafter. So that is the unit box function, and immediately from this we get that the Laplace transform of the unit box function is the same as the Laplace transform of h of a So if you look here, h of ab is the same thing as h of t minus a, because it turns on at time a, so it turns on at time a and it turns off at time b. So minus turns off at time b, which means that the Laplace transforms here using the formula above. The Laplace transform of h of ab is equal to, for this first one, you get e to the minus as over s, minus here you get e to the minus bs over s. And typically we'll just say that the Laplace transform of the unit box is e to the minus as minus e to the minus bs all over s. So that is the unit box or unit interval function in that case. There is one more formula that we probably need to talk about here, and it's just a simple corollary here. Notice that if we're looking at this, then the shifts match. If the shifts for some reason didn't match and you still wanted to take the Laplace transform, then the formula for that is the Laplace transform of h of t minus a times f of t is equal to e to the minus as times the Laplace transform of f of t plus a. Now, to see where that's coming from, notice that the effect that the transform has on f of t minus a is it adds a to it, because if you take f of t minus a and you add a to that, then that's f of t, which is what the transform is the function f of t. So it's the same thing here. I have the function f of t, and the transform, or the step function h of t minus a, is adding a to the transform. So I'm not taking the transform of f of t any longer, I'm taking the transform of f of t plus a. And so together, these three formulas completely describe, so the three boxed formulas I have on here, completely describe how to handle taking Laplace transforms of functions times unit step or Heaviside functions. We're going to be looking at another video coming up where we actually take the Laplace transform of a piecewise defined function by first turning it into a description involving Heaviside functions and then figuring out what its transform looks like. All right, thank you for watching.